So, Nathan, we thought we would start with asking you about being a pilot. We don't meet a lot of people who are pilots, and you are one of them. Can you tell us more about how you got into flying?
So I think it was back in 2013. I had a friend who was taking flying lessons, and that just really piqued my interest. Just sounded super fun. Like flying for me, it's like this perfect combination of science and technology. Like you really need to learn a lot about aeronautics and how airplanes work to fly a plane, at least to fly a plane safely. And then just skill, just raw skill. It takes a lot of skill to be a pilot. And then just adventure. Like it just feels really adventurous to just be cruising at 3,500 feet and you can kind of just go anywhere you want.
Was there
And so
was there any "oh shit" moment that kinda made you, like, question everything?
I would say close call. I had one moment which was a little spooky. This was my second time I ever soloed.
Mm.
So I was taking lessons in Palo Alto Airport. So I decided on this flight to fly like to the coast, and there's this like tiny little island with this like one building on it that's like 500 feet off the coast. And I just wanted to fly there and it's go down to 1,000 feet and circle it and then fly back. And I was actually on the way back. I was flying north along the coast. Usually pilots fly at some multiple of 500 feet. That's like the altitude you would
Mm.
achieve. But I figured I'll fly at not 3,500 feet. I'll fly at 3,700 feet because why fly at the altitude everyone else is flying? And so it's really hard to see. It's actually pretty hard to see other planes from the air. Like they can blend into the sky or the clouds and they're just really small. That's one of the skills you develop as a pilot. You get better at like just seeing other planes so that you can avoid the traffic. But anyway, I was flying at 3,700 feet and then all of a sudden in front of me, about 200 feet down from me, there was another plane and we literally were completely aligned. Like if I was flying at 3,500 feet, we would have like hit each other like nose to nose,
Wow.
presumably to avoid each other. So that was a little bit spooky, but not collisions in flying are incredibly rare. Like, yeah, especially now. Like I think in 2020, there's a new regulation that all planes need to have a new sensor in them. So it's called ADS-B. So you'll actually get notifications if you have planes near you, as long as you're near control tower, which most places are, unless you're like really out in the boondocks. But that was a weird moment. But it wasn't really like a close call exactly, but it was a little spooky. Certainly didn't stop me from, you know, continuing to fly.
So, you mentioned something called a spin training in one of your blog posts. What is that
Yeah.
in flying?
Well, spin training. Okay. So you don't have to do spin training as a pilot, but it is a situation you could find yourself in. So I did think it was important to at least experience it and know how to get out of it. So a spin in a plane, it's more of a tumble. So it's basically when the plane stops flying and it's just basically falling like a rock and it's tumbling like end over end. And so it's actually pretty hard to get a plane into a spin, especially like the Cessna 172 that I was flying. So you like really have to put a lot of effort to do it. It's pretty easy to get out of one as long as you know what to do. So, I asked my instructor to show it to me and beforehand I prepared myself. I looked at like like lots of videos on YouTube of people doing spins, but wow, nothing prepares you for the real thing. It really doesn't. It's so technically it's a stall with rotation. A stall basically means the wings are no longer flying, and then rotation means you're just rotating
Mm.
every which way, including inverting. And so you lose about, I think, 600 feet every couple seconds or something like that. So I think we started the spin at 4,000 feet maybe, and then by the time we got out of it, we were probably at like 2,000 feet. But yeah, you pull about, it just feels weird. It's like nothing else you've ever felt. One of the expressions I heard about it that I heard someone describe it as is as a roller coaster without rails. I think that's a really, but yeah, I mean, and then when you're getting out, so when you exit the spin, when you do the procedure, you're actually just vertically flying straight toward the ground. So then you have to pull up slowly to get out of the dive. And you pull about 2 Gs.
Oh, wow.
So that means you feel double your body weight at the pull out. So pretty intense. I think on that lesson, we did 4 spins and then, I didn't throw up, which was good. Although I do in the future, I do want to do like actual aerobatic training where you pull like, I think up to 4 Gs. I think 4 positive Gs. And sometimes you pull, I think negative 1.5 Gs. I'll most likely, I'll most likely throw up when I do that training. That seems inevitable because I don't have a great stomach, but aerobatic training just seems like super fun.
Is that where
Yeah.
you can then like do shows or
No, it would just be for fun. I wouldn't be,
impress
but
your date on the
yeah, I'll take
before
my
dinner?
date up. Right. But that's what you do, stuff like barrel rolls and hammerheads, loops and all sorts of fun stuff like that.
Right. Well, I don't do very well on roller coasters, so I'm not sure if I would be into trying that necessarily.
But I definitely recommend for everyone to do just an intro flight lesson, because like the first time, like you're not just in a small plane, but when the instructor tells you like take the controls and you can fly it, like it's an incredible feeling when you take the yoke and you just move it a little bit and the whole plane moves around you. Like it's really incredible. And yeah, I want to be clear, like so a lot of people think small planes are really dangerous because the only time you hear about small planes is on the news when they crash, but they're actually like very safe. The main reasons that small planes crash are pilot error. So one would be, believe it or not, one of the most common reasons planes crash is because they run out of fuel. Uh,
Wow.
is it's so stupid to me, because what you're supposed to do as a pilot is you have a checklist, you have a pre-flight checklist, and you religiously follow that every single time through all the checks of the plane, all the components, including checking the fuel. Like like what you do when you fly a small plane is you literally open the fuel tank and you look inside and you measure it. There's like a special stick used to measure. If you do that, you're never going to run out of fuel on a plane. So it's really like stupid error for a pilot to make, to just not go through the pre-flight checklist. And the other reason planes crash is a pilot flying into weather they shouldn't be flying into, which again, very easily avoidable if you just check the weather before you fly. Great resources to check the weather. Certainly that's not gonna happen on an intro flight. Yeah. I love taking people up for their first times in small planes. Uh,
Yeah, Rana is now down, but I have a volunteer,
Uh,
right?
no nosedives, no spins.
yeah. We want to. I might show you a stall, but we won't.
Okay, so coming back to the more technical chat. So for our listeners, how we actually met was during when Ronak and I were doing the bootcamp at Insight. So you came to help us out with Lambda architecture at the time, and you were building the Apache Storm and then writing the book on Lambda architecture. And yeah, so I think you would have been, you mentioned this in your blog post as well, right? Like you would have been very easy to just kind of build a company around it after that. But instead, you kind of took the other direction of starting Red Planet Labs. Can you walk us through how you decided to take that approach?
Yeah, well, store at that time, yeah, I mean, I was getting a lot of demand from people wanting like basically like consulting and support services for Storm. So I very easily could have started a company. That was a proven model, successful open source project with a ton of traction. Would have been very easy to raise money and pursue that route. And Storm did a lot. Like it really advanced the state of like scalable real-time computation. It was the first project to do that in a fault-tolerant way. And then also just like an easy way. It was very easy to use and do that kind of stuff. But like, I was always like thinking like deeper, like I really care about just like, I think what has always like really motivated me and really interested me about just programming in general. Like it's the only field of engineering where you can completely automate what you were doing before. And like instinctively, it seems like the work you should be doing should be whatever's unique to that thing. And you should otherwise be able to reuse every other piece of it. Right. And with backend development, it did not feel like that at all. And like Storm certainly helped for just creating the capability of real-time computation. But when you looked at just like what it took to actually build the backend for a product end to end, Storm didn't move the needle there, really, when you look at like the end-to-end cost. And that was the part that like really bothered me. And it was through working on my book and just developing like the theories of the book beforehand that I started to see that there's this different approach that could be taken, which really would move the needle and make it so that what it took to build a backend was closer to what it took to describe it. And like, just to like give an example of that, right? I like to use the Twitter example a lot just because Twitter is a very well-known product and I used to work there. So I know what went into building that product at scale. And so like the original Twitter consumer product, they reached scale in 2011. It was started in 2006. That's a product you can describe what it does, timelines, social graph, follows, retweets, hashtags, search, et cetera, et cetera. You can describe every feature of that product in a couple hours max. Not very complicated to describe all the different user experiences and flows that you go through in that product. But it literally took Twitter 200 person years to build that product at scale. So again, we're in a field that's entirely about abstraction, automation, and reuse. So how is it taking 200 years to build something you can describe in 2 hours? And it's not just Twitter. You look at any product, especially at scale, there's just huge disparity between how long it takes to describe it and how long it takes to build it at scale. And so this new approach that I saw the broad outlines of seemed to me something that could really change that, make it so that that cost would be much less and just fundamentally change the economics of software development. And so that really interested me and seemed much more important than building a company around Storm, which would have purely been about monetization at that point. You know, like I don't think Storm as a project was going to change the economics of software development to that extent, like not nearly to that extent. So that's why I decided to pursue Red Planet Labs and then just with Storm donate it to Apache and let it just be a pull-up.
How did that vision of Red Planet Labs, like, how did that evolve over time?
Yeah. I mean, basically what I started with and what took me years to figure out was what is a common set of abstractions that can express any application end to end with just that one. So it's like completely inclusive. It handles, everything in the backend that you need: data ingestion, processing, indexing, and querying. So basically what I started with and what I knew from writing my book and developing Lambda architecture. So I think the most important thing, which I explained in my book, was how to look at building software applications from first principles. Like when you look at how backend development has been done since the 80s, like the gold standard has been the relational database, right? And the relational database it's not based on the true first principles of backend development. I know that's going to sound sacrilegious to a lot of people who consider it the gold standard, but it's really not. Like what exactly are the principles of it? Like the idea behind a relational database is that you have tables, you have keys, you have columns, you have foreign keys. So that's the model, right? Now, can you say from that how that encapsulates all possible systems you want to build? Like it is very unclear. There's not a direct connection from that. So the first principle, which I showed in my book, it's so simple. And it so clearly encapsulates every possible system you ever want to build. And it's query equals function of all data. So any question, like a backend is all about answering questions, right? What is Alice's bank account balance? What is Bob's location? What is the total number of page views to this URL over a range of time, and so on and so on, right? And the most general way to ask a question is to literally run a function, an arbitrary function, over all of the data that you've ever seen, that your application's ever seen. So clearly that encapsulates everything you could possibly ever want to do with any system, right? That's clear, right? That's a much better starting point than the relational database model, which is arbitrary, right? And so in my book, so obviously you can't literally do that. You can't literally run a function over your 10 terabyte or 10 petabyte data set, whatever size it may be, every time you want to ask a question. So in my book and with Lambda architecture, I showed, well, what is the smallest set of trade-offs you can make to actually have a general model? And all you have to do is add the concept of an index. So query equals function of all data becomes indexes equals function of all data, and query equals function of indexes. And that does capture every single backend system that's ever been built. Now, with the way backends have been built since, basically for my entire lifetime, you're using different tools for each one of those pieces: data, functions, indexes, and queries, right? And so what I was looking for when I started working on Red Planet Labs is, well, how can I generally meet that model? Like build a general purpose system where you can have arbitrary indexes, arbitrary ways of computing those indexes, and arbitrary ways of doing those queries at scale with a simple set of common abstractions that compose together into any application you want to build, whether it's Twitter or Google Analytics or a bank or what have you. And it took me a long time to figure that out. But that's basically what I started with. So I had the general model, right? Indexes equals function of data and query equals function of indexes. I also, the other thing I had figured out by that point was just like specifically on indexes. So when you look at how databases work, they're actually all narrow. Like there's no such thing as a general purpose database now. They all have what they call a data model, and that's all it can do, right? So you can have relational, document, graph, column oriented, like, and so on and so on. And so that indexes data in a very specific way, and then it has very specific ways at which you can go about querying those. And what I realized back then was that a much better way to express indexing is as data structures, not data models. And in fact, every data model is just a particular combination of data structures. Key value is just a map. Documents, a map of maps. Column oriented is a map of sorted maps, and so on, right? And so I knew at that point that the right way to express indexes was as data structures, so that, to build an application, you'll need to build many indexes, and each one of those can be shaped exactly as you need it to meet every individual use case of your application, which is a big problem that you see with backends that are using databases, which is every backend right now. But as soon as you choose to use a database, which you have to now, not that it's really a choice, but the moment you choose to use a database, you have now created a lot of inherent complexity in your application, because you have to twist your application to fit that data model. And there is no data model that will fit your application perfectly. And this is like the first and possibly the biggest impedance mismatch which you take on once you, like at the start, like as soon as you start your application. And so that's like a huge problem and a huge contributor to complexity. The fact that you can't actually model your indexes exactly like you need to for your application. So that was the starting point. So I knew the general model, indexes equals function of data, query equals function of indexes. And I knew that indexes should be expressed as data structures. Then I knew that, to actually build a full application, you'd be materializing many indexes of many shapes. And probably wasn't until I'd say 2016 that I was confident that it was possible, that I had figured out what the abstractions were. So it was pretty difficult, to say the least.
In some of your posts, you mentioned this idea of suffering-oriented programming. Like, what
Yeah.
was that one of the key principles that you thought about too when you were starting to build Red Planet Labs? Like, how hard it is to build these packages?
Yeah. Well, the suffering phase was everything I did before Red Planet Labs. So everything I'd ever built, and also everything I'd ever helped people build, right, through my open source work. The idea behind suffering-oriented programming is that, don't build abstractions in the abstract. Don't build an abstraction until you have suffered through the pain of not having an abstraction, and what are all the use cases that such an abstraction would need to fill, and all its weird permutation. So certainly I had experienced that beforehand, just building scalable systems. I call the current approach the a la carte model, right? Which is you pick different tools for different parts of your system, and then you get them to fit together. And I had certainly experienced how fundamentally flawed the a la carte model, according to some of the things I just described, with the fact that a database is inherently flawed, how you have to twist your application model to fit the data model, and so on, and just other problems with getting things to integrate together. So yeah. And so basically building Red Planet Labs and building Rama was like suffering oriented programming on steroids, where my list of use cases was literally every application that I'd ever worked on or ever helped working on. So it was a pretty expansive, just set of use cases I had in my mind, trying to unify them together into a common set of abstract.
So you recently announced Rama, which is the platform, or as you describe it, it's the 100x programming platform. And we want to talk more about Rama. Before we get there, you started the company in 2013, and you mentioned that around 2016 is when you kind of found the right abstraction to start building on top of. What did that 2013 to 16 period look like? Because if I remember correctly, you hadn't started a team around that. Like, you were the one doing all the research yourself. So yeah, can you tell us more about what that phase looked like?
Well, I didn't fundraise and hire anyone until 2019. So 2013 to 2016 was a lot of me sitting at my computer, staring into space, thinking, and a lot of just, I had like this one big text file where I was like, kind of just like exploring, like stream of consciousness, just like, here's an idea. Let me work through it. Let me test this idea. Let me test this idea for an abstraction against all these different use cases and see what happens. And just like very slow process of kind of getting closer to what the right abstractions were. I think the main thing I had to figure out from 2013 and 2016, there's actually a new programming paradigm underneath Rama. And actually when you use Rama's, like Rama has a Java API, it's just a regular Java API, but that API is actually expressing a subset of that programming paradigm. Basically the programming paradigm, it's actually like a general purpose programming paradigm, a new one. It's basically like data flow programming, but generalized into a general purpose language. So you can do all the things you can do with a regular language, like variables and conditionals and loops, you can do in data flow, but it's expressed differently. And data flow is a great abstraction for doing distributed programming, as we already knew at that point from data flow tools built on top of things like Hadoop. And so what Rama is doing is it's general, like way generalizing the idea of data flow. And so a lot of that work from 2013 to 2016 was discovering that programming paradigm and seeing how that, how things would fit together to be able to just express arbitrary applications.
Like, were there stuff that happened like in that time period, all the way leading up to 2019, maybe that like, new technologies that came along or, getting more adoption, like did that kind of impact your interests as well as like how you think about the problem? Because, right, like I feel like one of the reasons why Lambda architecture caught on and all these applications became a thing is because storage got so cheap, right? Like in distributed compute, like without those sort of advances, it's very hard to kind of ditch the database, right? So to speak.
Yeah, for sure. And I think the big thing was storage becoming cheap for just like enabling these other ways of building things. And that was the case well before 10 years ago, right? That was the case 20 years ago, like when like MapReduce became like the thing when that was the robot thing, right? I don't think there has not been any fundamental advance like that in the past 10 years. Obviously there's been a lot of innovation, a lot of new tooling, but everything is still working under this. Everything is still doubling down on this a la carte model. To build a backend, you're going to have a dozen or 2 dozen or more different tools that you're actually using and fitting together in some way where you're still like, everything is still very narrow, very specific, and forces you to take on these impedance mismatches, like I described with data models for databases. So nothing in the past 10 years changed. Ultimately, like what I was doing with Red Labs and Rama was a really fundamentally different approach to the way software has been designed for like my entire lifetime, to actually have one tool based on a simpler set of primitives that can compose to all these other things that people are doing with specific tooling and able to build your backend end to end on a single platform instead of a dozen different platforms.
So Ronak asked the serious and the good questions here, and I asked like the really dumb and trolly ones. So to stay on brand, like, right, maybe one silly thing would be like, oh, the generative AI gets so good that like, now you have these bloated software, but it still somehow works, right? Like you just basically be able to write all this like crappy code, but maybe you have some ways of like performance test it such that, you can still kind of package it up such that you don't necessarily, well, okay, I think I sounded smarter when I started than when I'm finishing.
So I'm wondering like, what's like AI programming? How does that affect?
That's the better, smarter question to ask.
Yeah. Well, AI programming is still in its stages.
Right.
It's certainly capable of building a backend end to end for you. I mean, I think AI is ultimately going to be limited by the same things that limit human intelligence. I don't think it's like magical. And I think if you have a much simpler set of primitives that you're building upon, I think AI will do a lot better. And if you're using a dozen different tools that creates all this complexity, that's going to make it a lot more difficult for AI to reason. And it's still going to be difficult to operate in production. Like one of the cool things about Rama, because it's such a cohesive general purpose platform, it's a much better target for AI for building backends than, the hodgepodge of a million different tools that you have to use. currently. So I'm actually really excited to explore that in the future.
So
Like after paying me the price for the ChatGPT premium, like that is one thing I noticed quite a bit is when you ask it to do stuff, right? Like it's a lot better at writing out the intermediate steps, which to our point here translates into those more generic sort of models before you continue on. I see.
Right.
So like one way I'm thinking about Rama is that you're saying instead of instead of an engineer going and saying, I want to use a relational database or I want to use the specific messaging queue or whatever the technology may be and build around that, you're saying, let the engineer describe with the abstraction that Rama provides what it is that they're trying to do. And the tool behind the choice, whether that's say a relational database or a key value store or whatnot, that's an implementation detail. But what stays the same is the abstraction or the use case that the user is describing. Is that the right way to think about this?
Yeah, let me describe what Rama is.
Yes.
Let's take a step back.
Yes.
So you're not using database when you use Rama. Rama's doing all that stuff with a simpler set of abstractions. So everything that like a database does, Rama's doing for you. You're not using any other tools. Like Rama's doing everything. So there's basically I'll describe the Rama's programming model. So again, like I described the first principles of building backends, right? Indexes equals function of data, and query equals function of indexes. And that's basically the programming model of Rama. So you have 4 concepts, right? Corresponding to each of those things and those first principles, right? So you have the first thing in Rama is called a depot. That's how data comes into it. And a depot in Rama is a distributed log of data. Think of it as, it's actually exactly like Apache Kafka, but built in and integrated into the system. Then you have ETL topologies. Again, all this stuff is inherently distributed. So ETL topologies consume data from depots as a stream and then do computation on it and then produce indexes, which are called partition states, which is the next concept. And we usually refer to partition states as P states. And partition states are how you do indexing in Rama, which as I described before, it's in terms of data structures. So to build an application, like if you look at our Twitter scale Mastodon instance that we open sourced, in one of the modules that's doing like the core stuff, so profiles, timelines, fan out, and all that stuff, I think there's 33 P states with a huge variety of data structure combinations between them. So when you're building an application of Rama, you'll materialize potentially many, many P states, all again, completely fine-tuned and shaped to precisely what you need for your application. And then the last concept is querying. So how do you actually query your P states? So there's 2 ways to query in Rama. So one are called point queries. So that's when you just want to fetch information from one partition of one P state.
Yeah.
And it uses this, what's called a path-based API. So these P states are arbitrary combinations of data structures. And so we have a mechanism. So it's very easy and concise to reach into a P state, regardless of how complex the structure is, to retrieve a value or some aggregation of values. The second kind of query is called query topologies. And these are predefined queries that can look at any or all of your P states and any or all of the partitions of your P states. And it's basically a real-time, on-demand, distributed computation looking at all of that stuff. So you can do some really powerful stuff with query topologies. So query topologies would be analogous to like a predefined query in like a SQL database, for example, except it's defined using the exact same API that you used to define ETLs, which is the regular just Java API. And it lets you reuse code between both contexts as well as just being generally a lot easier to just manage because it's all this, it's not using some bespoke system or registration system like you would in a SQL database. So those are the main concepts. And you can see how it's literally just the first principles, right? So indexes equals function of data. So that would be depots, ETLs, and P states. And then queries equals function of indexes, which is just the 2 different ways of querying P states. What was your original question?
I was basically trying to think about how, as an engineer, like when we're building these backends, we are so used to just thinking about, okay, think about a data model because, well, that's what we have been doing. Well, if you pick, let's say, a relational database, well, you got to have primary keys, foreign keys, rows, and columns. If you pick a key value store, then, okay, depending upon the kind of data store you choose, you will be limited by some of the features you can build, or you might have to kind of re-implement some of that in their code. So when someone's starting to now use Rama, for example, in a way, should they just stop thinking about like databases, for example, and think about what do I want my applications to do? And let me define that data structure and whether Rama stores it, how it stores it, what data structures it uses under the hood. Like that's implementation detail for the engineer. So that's what I was trying to figure out.
Yes. So you're liberated as a programmer using Rama because you're no longer restricted by your data models. No longer have to twist your application to figure out how can I fit it into this data model. So again, Rama's P states, it's just data structures, right? So if you want to use those data models, okay, well, that's fine. Use that data structure combination. If you're going to do something else, if the optimal way to meet that use case is a different data structure combination, well, now you can do it instead of having to twist your application. So like, for example, so basically the way to approach developing a Rama application, I actually have a great, on the Rama documentation, which is on our website, on the last part of the tutorial, it goes through this process. The last part of the tutorial is building like a Facebook style social network from scratch. So like bi-directional relationships, like a post, like a wall for every user with posts and stuff like that. It only ends up being 180 lines of code at the end of it to a fully scalable like social network. And it goes through the process, right? So the where you start is, well, what are the queries I have to do? What are the questions I need to be able to ask? And what's the data coming in? So for something like a social network, it would be like, who are the followers of this user? And I need to be able to ask that in a way such that I can paginate through them, right? Because someone might have 1 million followers. Or likewise, who are the friends if you're looking at like a bidirectional thing? What are the friend requests? What is a page of posts on someone's wall? Like, what is someone's profile, right? What is someone's age, whatever, right? Or maybe you have an analytics query in there or something, right? Like, how many users signed up per day or something like that. So you start with your questions, right? And because ultimately what an app is, right?
Yeah.
What are the queries I need to support? And then you think in terms of, okay, well, what's the data I have coming in? So you have things like account registration, friend request, accepting a friend request, making a post, and so on and so on, right? So then the first step is to actually start with the P states. So, okay, well, what set of P states do I need? What data structure combinations do I need to be able to answer these questions? And then what does it look like to ask those questions on these P states? So it might be that one P state you create can answer 10 of your questions, and another P state might exist only to answer one particular kind of question. So like to give you an example, like if you looking at who someone's followers are, and you also need to be able to say like, how many followers does someone have? Does not just looking at someone's followers, but also just asking, does user A follow user B? Like these are the kinds of social graph questions. So all of that can be supported with a data structure, which is a map to a linked set. So a linked set is a set that also remembers the order of insertion. And so you can do this with Rama. So like in our master implementation, we have the followers P state is a key to linked set. It's a map of linked sets. When you want to get the number of followers, you just get the size of the inner set. And even if the inner set has 10 million elements in it, it's still a fast, like, less than a millisecond operation to get that. If you want to paginate through it, then you're just querying that in order. You're doing range queries on that inner set. If you want to ask if user A follows user B, well, that's just a set membership query, right? And all the stuff you can do very, very, very easily with Rama. Whereas if you look at like a different part of the application, like personalized follow suggestions, well, that's a completely different P state with totally different indexing, right? And then once you figure out what your P states are, what the queries look like, then you look to see, all right, how do I materialize and maintain those indexes from my data that's coming to my depots, like follow requests, accept follow requests, making posts, etc. Right? And that's where you write your ETLs to actually, right? You're making a function from data to indexes. So that's the mindset, I guess, you use when using Rama. And the great thing is that you're able to do all this stuff, all this flexibility on top of a single platform. And one of the really nice consequences of this is how much it simplifies deployment. Like when you look at like companies building applications at scale, like the front-end engineering is no joke. Like it is really costly. Like you often have entire teams only doing that, writing sometimes millions of lines of code and configuration. And none of that code there's no business logic in any of that code. It's pure complexity.
It's plumbing and putting bits on boxes.
It's crazy. Like it's really wild. Now with Rama being such an integrated platform, when you can deploy your whole thing on one system, well, Rama understands how to deploy and update Rama applications. That's like the core parts of the platform. So it's able to do it in a general purpose way with all the best practices just built into the system. so that you can take an existing application that you have running, which is called a module in Rama, and you can say, I want to update it. And it's we spend a lot of time on module update. So it's completely fault tolerant. It does the transition very, very smoothly to transition responsibility between the two versions. All the stuff people are doing manually and very, very complex way currently. So all that stuff is just free because it's a general purpose platform. It's able to implement it in a general purpose way, and then boom. Now, as a developer, you don't really have to worry about that anymore, which is I think one of the most brutal costs of the a la carte model is the fact that you have to engineer deployments yourself.
Oh, for sure.
Now the other really nice consequence is monitoring, right? So Rama being such a general purpose platform, it's able to implement monitoring. Monitoring is the same thing, right? Monitoring is you're collecting data, you're materializing views on that data, and then you need to have a way to query that data. So Rama actually implements monitoring using itself. So there's a built-in Rama module, which collects data and then materializes telemetry on that data it's collecting the data from all the other modules and then materializing views on that data. And then it has a built-in cluster UI where you get very deep and detailed telemetry on all aspects of your module, or of all your modules, I think it's really cool that it's able to just be recursive like that, right? Rama is just using itself to implement telemetry. It's not doing anything special. The telemetry module is exactly the same like any other module. So that's, just to finish the story, right? So how much Rama helps on deployment and monitoring. I was always thinking from the start in terms of end-to-end cost, and deployment and monitoring are a very substantial part of end cost.
Yes.
So that's one of the things that really excites me about Rama, that all of that complexity is just gone when you're using Rama, and it's so much simpler, so much easier.
I think it's super cool that you guys literally built a Twitter clone in order to just show how powerful it is. And just to quote some numbers, right, from the blog, that it was only 10,000 lines of code comparing to the 1 million that Twitter wrote to start with. And then this is having 100 million bots posting 3,500 times per second at 400 average fan out, which, sounds super impressive. The other aspect, right, you measured is to sort of quantify this 100x improvement is how long, right, it took to do it. So 9 months versus the 9 person months versus the 200 person years. Yeah. So I'm very curious to learn more about the trade-offs. So in terms of the pros, so in addition to deployment and monitoring, as you mentioned, I imagine this is a bit harder to do, but I imagine bugs are also become less and much easier to fix, right? Because I mean,
Yeah.
a lot of the production bugs are sort of happen in between kind of systems that sort of come out of this a la carte menu that you described, right? So if you actually start from scratch, if I may, I feel a very maybe bad example is going from a dynamic language like Python, where you don't have to learn to know a lot, right? To a compiled, actually strongly typed, where you have to kind of specify all the things up front. You get that trade-off, now there's way less, random things can happen, right? What do you think about the debugging and then, the outages, that aspect of things?
Yeah. Well, like, first of all, bugs become much less when you have 100x less code. You're gonna have a lot less bugs.
Actually, no, that's
Uh,
right. No code, no bugs.
it's not just the line. It's not just the number of lines of code. It's just the reduction in complexity. And again, when your code is actually doesn't have impedance mismatches, when you're able to actually represent data in a way that actually is optimal and makes sense, as opposed to having to twist it like you do with databases, that reduction in complexity just helps a ton, right? But of course, you're still going to have bugs. We had bugs in our massive implementation that obviously we worked them out before we deployed it, but work them out in the same ways that you would work out bugs in any system, through testing, right? That's actually another aspect that really helps with Rama, is just how much easier it is to test, because you don't have to think about, oh, how do I start up these 10 different components, create them with mock data and all this stuff, and get them to work in a test environment, which is all within a single process. So Rama provides something called in-process cluster, where you can simulate a Rama cluster in process, and they can use that just like you would a regular cluster, deploy models to it, add data to it, do queries, whatever. So that's how we test it. If you look at our massive implementation, like we've written a lot of test code using that exact same approach. We deploy modules, we pen data, and then we do a search on what happens afterwards. That helps a ton. Then of course, when it comes to if you actually have a bug in production, well, again, like it has module update built in, so you just update your module and fix the bug. So I'd say that all that stuff on multiple different fronts, reduction in complexity, the ease of testing, makes it much easier to build like quality software. Like we actually look at how like backends are built today, like backend programming, especially at scale, it's gotten so complex. It's beyond the realm of human understanding. Like there's no one working at Twitter or Google or Facebook or any of these services that really understands what's happening. Not to say they don't understand, but it's so complex that like you can only understand things like empirically, right? So like based on what I'm observing now, that's what I understand. So it's not a surprise at all how buggy all these different platforms are. Like, isn't it crazy that when you like every one of these services you use, they have bugs on them all the time. And they have billions of dollars and thousands of engineers. How come they can't fix? Sometimes the bugs are like brain dead. Like, how is that even a bug? You know? And these are the companies with good engineers, right? Not to mention the companies that are, weaker engineering team. How are they so buggy? Like such visible bugs in a consumer product. And it's just because it's impossible to comprehend these systems because they're so complex. Because you can describe what these applications are doing again in 2 hours, but they've invested hundreds of person years in developing them. So like there is a big complexity problem in software, and more than anything else, that's what Rama is tackling, is this extreme reduction in complexity. Like what Rama's doing is it's just, you're able to do things in a way that avoids the complexity that people have been taking on for decades. And it's not like it's doing anything magical. It's really about what you're not doing with Rama, which you're forced to do when you're kind of doing stuff the traditional way with the model.
Like going a little bit meta. So in the process of building out this Twitter clone, like did it change some, I don't know, like code in Rama itself of like basically where you draw like the boundaries between different concepts and things like that? Did it have any?
No. Basically, you just use Rama as is to develop.
I see. Cool.
Just because the model is, the model makes sense. It is general purpose, right? Query equals functional data, right? Expanded to index equals function of data, and query equals function of indexing. Like that's the model, right? It makes sense. It's general purpose. It clearly encapsulates all systems, and that's the model using in programming Rama, right? And so, building Twitter was one application of that model. We could have built anything else, right? We specifically chose Twitter just because we were familiar with the actual implementation of Twitter. And so we could do like a comparison against costs.
So,
and when you actually look at like Twitter, like why was it so expensive for them to build? And the reason was one of the main reasons was because of just how much specialized infrastructure they needed to build over the years, because they needed to represent their social graph and there was no tool which could do that the way they needed it. So they had to build it from scratch. They had to build multiple other databases and services from scratch. And in all of these things, they were like, a lot of stuff is repeated, right? So when you build the database from scratch, well, you're repeating a lot of stuff. You got to build replication again, which is insanely expensive to build, by the way, and also insanely difficult. And you got to figure out durability and like distribution, how things network and talk to each other. That's just being repeated over and over, right? Like the one mantra everyone knows from programming, like from really the start being a programmer, is do not repeat yourself, DRY.
Yeah.
And it's completely non-existent in backend programming. Like as an industry, we are repeating ourselves constantly by the fact all these systems are actually doing the same things, or they have a lot of their subsystems, such as replication, are having to do the same things. Sometimes they're doing it in different ways sometimes, but they're trying to solve the same problem, right? So with Rama, with a true general purpose system, we're able to implement replication for Rama, which is something we spent a lot of time on. And now it encapsulates all possible ways in which you might specify these computations or indexes. That makes sense.
So one thing I'm thinking about is like, when we look at any of these apps today, the complexity grows over time because like a majority of applications start with an API backed by some database that is fine for the prototype. If the application
Yeah.
works out, you need to grow out of that single database. Either you shard it, you build different views for the same set of data. Like sometimes, as you mentioned, you want to represent it as a graph, sometimes a key value store and whatnot. And a lot of time backend engineering teams spend is doing migrations because either the amount of scale you're hitting, your app cannot handle anymore, or you want to provide a new feature. And for that, migrating to, let's say, a new system is going to be much better. What does that look like with Rama? Like if you wanted to represent your data differently, would you just go create a new P state or like, does it also ease the migration piece?
So yeah. So if you need a new view of your data, then you can just build a new P state. So you can always read whatever, read as much. You can start constructing a P state by looking at the start of a depot or just at some point in the past of a depot. There are other cases where you might want to actually change your existing P states because you want to change the format of something. So you can do that manually now with Rama, like through a module update. Although we are currently working on a first class migrations feature where you would be able to just take an existing P state and then just change the structure, right? So maybe like instead of using this data type for this value, you want to use this new data type with maybe more fields in it or less fields. So that's coming soon. And then there's like another level of it where you might want to not just migrate each partition of a P state, but you might want to actually include some repartitioning of that during the migration. So actually change where stuff is stored, not just how it's stored. So all that stuff is coming.
That's pretty cool.
Still doable to do. Yeah, it's still doable to do right now. More manual, but we'll have some first class for that soon.
I see. And so double click on deployments for a second. And this is just me trying to understand this better. So if I look at an existing application, it's like we went through this whole microservices and whatnot, but eventually what it means is you have your data store running on a set of machines, your web services running on a set of machines, your Kafka queues or some other queues running somewhere else. And maybe you add other pieces to your ecosystem as the app grows. So if I think about building a Rama application, if I just look at it from bits and boxes perspective, what binaries get deployed where, and how do you scale this thing out once your app keeps growing?
Right. Yeah. So first of all, I think before we go further, Rama doesn't have to be used in isolation. I think some people may get the wrong impression of that. Like when you're using Rama, it doesn't mean that now everything has to be built on Rama. So Rama can very easily integrate with other systems, just like you do with any other system you use, a la carte architecture. Very, very simple to if you want to integrate with, want to use a database from Rama, very, very easy to do. Or likewise, you can also, Rama can consume data from external queue systems, right? So we actually have an open source project called Rama Kafka, where you can use Kafka as a data source for your ETLs. And it works exactly like you'd be using a depot. But more generally, in terms of deploying Rama itself, Rama runs as a cluster. So it has a central node called the conductor, which is, the conductor doesn't do any it's not involved in data processing. That's just how you do module operations, like deploying a module, updating a module, or scaling a module. And then there's a cluster of worker nodes that all have a daemon on it called the supervisor, which just listens to the conductor for assignments. So what workers or what modules should it be running on the machine? The supervisor is responsible for starting and stopping worker processes as dictated by conductor. And so when you deploy a module, it's just a one-liner at the terminal where you tell conductor, here's my jar with my code, here's the module I want to run, go, right? And here's the pallets I want. And the conductor will figure out which supervisors to run that on. And then likewise, when you want to update, it's the same thing. You tell the conductor, I want to update this module, here's the jar, and it goes ahead and does that process. And same thing with scaling, where this time you don't have to give it a jar because you're not changing the code. You can tell the conductor, here's the new parallelism settings I want, and then that launches the scaling process. And when you're scaling, when you do an update, it's going to deploy to the same set of nodes it's already deployed on. So it's a co-located update. When you scale, you actually need to move data across nodes because now you're spreading nodes. But again, all that stuff is behind the scenes and transparent. So scaling will take longer because of the data transfer step, but it's all like very, very simple to do. It's just literally just like you just say, here's how many more resources I want, go, and then, it takes care of the rest.
And by the way, I'm just trying to figure out, is there a limit to how big a cluster could be? Perhaps looking at the open source Mastodon example you have, is it possible to share like on how many nodes is that running today?
Well, so full Twitter scale would take about 600 nodes.
That's it.
Uh,
That's okay.
yeah.
That's little for what I was thinking. With that's good to know.
Yeah. And it's that full Twitter scale would be 7,000 tweets per second at 700 average fan out. Again, with a very unbalanced social graph. But actually, the key thing for Twitter is in terms of scalability, or just in terms of performance usage, is the average fan out as well as the number of tweets per second. So I mean, we went into this in depth in our blog post about our Mastodon instance. So there's a lot of stuff you have to do in regards to having an unbalanced social graph in terms of achieving fairness and whatnot. But in terms of resources needed, it's really just about average fan out and number of tweets per second. And yeah, it'd be about 600 nodes to do that whole product.
That's pretty cool.
The consumer product. We're just talking about the consumer
Yeah.
product. I'm not talking about like all the other stuff that Twitter does. So we're looking at Twitter like circa like 2015, let's say, in on the consumer side of things. So the dominant cost of Twitter or of that deployment would be storage, because you'd be absorbing like, I think it would be like 5 or 6 gigs per node per day of like new tweets. And so, you'll need some pretty big disks on those partitions.
So like when thinking
Yeah.
about scaling, usually today teams scale different parts of the application depending upon where the bottleneck is. It's like, well, if your API isn't performing, let's look at the bottleneck. Is database, or is it just you don't have enough instances and you're chewing through too much CPU? With Rama application, like what does that look like? Do you also look at the same factors you would in a la carte model, or you just scale the entire cluster and Rama figures out what to put their storage or compute and whatnot?
Oh yeah. Well, I mean, it's all about telemetry, right? Actually finding where the bottleneck is. So that's where like Rama's built-in telemetry is really useful. And that was very useful to us developing our Mastodon instance to actually find where what were the hotspots in performance. So you look at things like, we just look at like for a P state, how many writes is it having per second? And what is the average time of those writes, or what's the distribution of it? And that stuff helps a lot to find where the bottlenecks are. You can also look at skew. So telemetry lets you look at not just like the overall picture for a P state, but also partition by partition. So one really common reason for a bottleneck would be skew. So this one partition has it's the load of another one, and that's going to slow down the whole system because you have some resources idle while another one is very right. And that is the main issue with the unbalanced social graph, is it's inherently like extremely skewed. So that's why we put a lot of effort to balance the processing, even when the social graph is so skewed. And that by the way, this Twitter obviously went to the same thing. A lot of their implementation is also trying to deal with that inherent skew. So a lot of things we did was similar to what Twitter did, but obviously in a more integrated way, in a much simpler way. And we ended up getting, like we did one optimization to reduce variance between tasks in terms of okay, so like, let's say you have someone with 20 million followers. If you're processing all their fan out just from one partition, that's going to be very skewed, because whenever that person posts a status, suddenly you have 1 million units of work. Whereas with normally per second, you have whatever 7,000 times 100 is, right? Which is a lot less than 20 million.
Yeah.
So that person creates a huge burst of load, right? And it's creating a huge burst of load on one task, right? So if you do the naive thing of just processing all of someone's followers from one task, you're going to be super skewed. That's going to massively slow things down. Because now that one task needs to work through a queue of 20 million things, whereas everything else is much smaller than that, right? And so one of the things we did in our implementation is we basically have a different view of the social graph specifically for fan out. So when someone has a lot of followers, their followers get spread around all the partitions, so that when you want to process that person's followers, you do it in parallel partitions and you balance the processing. For fairness, such that that person posting doesn't delay everyone else, per iteration of fan out, we only will process up to, in our implementation, with 64,000 followers per user per iteration, right? One iteration takes like 500 milliseconds on average, right? So to process all of someone's 20 million followers will take a few minutes, right? But that's the trade-off you have to make, because the number of resources you have is fixed at any given point in time. So that's, again, that's not on the Rama side, that's on the Mastodon implementation side. That's how we utilize Rama. We're able to do these things like materialize multiple views of the social app for different purposes. And, all these things we did, there were other things we did to reduce variance. When you reduce variance, you increase throughput because you have more balanced processing. And so you have less situations where you have some resources idle while another one is really, really busy. And there's actually more we could do on the massive implementation to actually reduce variance even further. But obviously we got the performance to a point where it was as good as Twitter, actually better than Twitter in many respects. So that, we didn't feel it was necessary to keep developing it. But we could make it, if that was a little bit more work, we could probably squeeze another like 5 to 10% more, but
Wow.
out of that. But obviously it's already a very, very high. But, so.
So like this is a different way of thinking about how you build backends. And as you mentioned, this is very different from a la carte model. You have a platform that is truly generic. So how are you thinking about adoption here? Like for companies to adopt this to build massive scale systems, usually the thing that many teams or engineers start was like, let me just hack on something, put a database in front of it, and I'll go. So how are you thinking about Rama getting adopted?
Yeah, that's a great question. And actually a lot of it I learned, a lot of this, how I'm approaching this, I learned from the open source work I did before, especially with Storm. So my general approach to adoption is the bottom-up model, which is as contrasted to the top-down model. The top-down model, which would be where you try to drive adoption through, you talk to CTOs and VPs of engineering, and you try to convince them to give it a shot. So outbound sales, it's very expensive because you gotta literally do it one by one, right? So what's much more efficient and I think more effective, and this is what I did with Storm, is the bottom-up model, right? So you make something that's really compelling that gets engineers really interested in it such that they try it out themselves without you even knowing about it. And they become your salespeople for you at the company that wish they were. That's what I did with Storm. That's how I was able to get Storm to be such a big project just by myself. And that's what I'm doing with Rama. Now, there's a big difference between Rama and Storm. Storm was like, it had like 2 concepts in it, and it wasn't that different from what other people were doing. It was just doing it in this, fault tolerant way. It was very easy for someone to pick up Storm and try it out just because there wasn't that much to learn to pick it up. Rama is different. Rama is a paradigm shift. Rama is a major, major paradigm shift. So it has a much, much higher learning curve than something like Storm or really anything else that you would look at. So that the high learning curve makes it more difficult to get adoption just because there's this upfront cost where you actually have to learn it before you can really start using it. And so that's why we launched the way we did. We started with this Twitter clone running at scale in this ridiculously small number of lines of code to basically create the motivation to put yourself through that learning curve where, oh, here's this thing. It's doing something really unusual, like literally reducing the cost of building this major service by 100x. And so, my theory is that would compel a lot of people to want to benefit from that. And what I've been seeing, like in these first few weeks since we've launched, is that message has gotten through to the early adopter type of people who base their decisions on the technical merits of things and like what is the value it provides, as opposed to like a later adoption kind of crowd where they base their decisions largely on social proof. So I want to use, like, I've been like, someone like that is saying, oh, I want to do something that's similar to what someone else is doing. Like, I literally want to see my use case done in a similar way already before I use that thing. Obviously, that's a much less technically savvy crowd. It is a big portion of the crowd, and that stuff is important. Like, you did need to be able to show those things. Right now, obviously, we're focused on early adopters. And the main things I've been seeing from like early users and like the early enthusiasm I've been seeing is from people who, it's like 2 things. So people who have systems that they need to scale, and maybe they've been through it before. So they have a lot of anxiety about what they're going to go through to scale their existing systems. Right. So they know how painful it's going to be to do the a la carte model, to use a dozen different systems and so on. And the other thing I'm seeing is people who are sick of these impedance mismatches for their whole careers. For 20, 30 years, they've been having to twist their model into these data models. And they understand how much complexity they're taking on from the get-go. And so that the idea of p-states, of being able to tune and shape your indexes to what you need as opposed to the other way around, is very compelling to them. And so that's like the general approach I'm taking. And so like over time, like right now we have as a demonstration, we have this one example, right? This Twitter scale Mastodon instance. which actually inside of it is actually like 20 examples because there's like 20 different, or, I mean, there are so many features in Mastodon, right? And they all work completely differently, right? But it's always just as one product, right? So over time, like as we are working with the early adopters and helping them achieve like massive success, well, now we're going to have more examples to show. And I expect that'll help Rama break through to kind of later adopters who need that social proof or need to see like Rama used in a way that's similar to their needs before they can give it a shot. So that's like the way I see adoption. So I don't anticipate it being that fast just because it takes time to build that social proof. But I do, especially with like how much early enthusiasm I've gotten, I do expect us to get.
It's really cool. And taking a step back, for you personally, how do you see this transition going from, right, like you're in your, you're somewhere by yourself, like, going through that big text file that you have, right? And then really thinking really deeply about these like really challenging problems to now more kind of like day-to-day running a company, having to manage people and then having to think about marketing, right? Like talk to developers. Like how has that transition been?
Yeah. Well, there's basically two transitions, right? I went from by myself in 2013, and 2019, I fundraised and built a team. So that was a big transition, learning to like manage a team and do all that, right? And I learned a lot. In the past 4 years, I've learned a lot about that subject, right?
Can you share
And
some
now
bits there, like the aspects that you learned there
about management.
about management and just building a team? I mean, there are a few parts involved, right? Like you went from having a problem you wanted to solve. You spent some years researching, trying to kind of better frame the problem and figure out a direction you want to take. Then you're at a place where you're able to describe that problem and fundraise, which is not an easy thing to do. And you're trying to solve something which wasn't done before. This is something new, a new paradigm in how you build software applications. So part of it is also selling in a way, like you're trying to show what you're trying to build, fundraise, and then build the team. So there are many pieces there. You can
Well, fundraising, learning to fundraise was its own thing. And it's kind of a weird thing because it's kind of fake.
say more.
Fundraising. 'Cause yeah, fundraising is you're selling a product that doesn't exist yet to people who are not in your target market, right?
Yeah.
That's what fundraising.
Yeah.
Like the investors are, especially for, I mean, for something like this, like deep tech, like, intended for serious software engineers. Like, I mean, some of my investors have a software engineering background, but they're certainly not doing that anymore. I don't think any investors were like that hardcore of engineers, except for maybe Max Levchin. Max Levchin is pretty hardcore, and like, yeah, he was a very difficult one to fundraise from, but he probably grilled me harder than anyone else in terms of like the technical details of Rama. He actually was very interested in the underlying language behind Rama, which no one else was interested in. But anyway, still the principle remains, right? Investors you talk to are not in your target market. And also they just don't really understand what you're doing. They don't really understand. Yeah. I can describe it at a high level, 100x cost reduction, build Twitter or any other application on one platform instead of a dozen. Like I understand that, but they don't really understand, right? So fundraising has its own art, its own like, yeah. My fundraising went really well, but I will say until it started going well, I thought I was going to fail. I thought I wasn't going to fundraise.
That sounds like fundraising.
Yeah, like I had I was as successful as you could possibly be. I raised more money than I wanted at a much better valuation than I was initially seeking. And then I got every investor I wanted.
Wow.
And
why was that?
It went spectacular.
Why was that? Like, do you know what aspects played a role in that being, like fundraising being as successful as it was for you?
I know every aspect that went into being successful, but again, I thought it was going to fail until it started going well. And also, like, it's not like I thought it was going to fail for a long time. Like, I got the whole round done in basically 1 month. But man, it was not looking good for a while. Because it's like, yeah, I mean, this is a whole topic, right? But like, especially with venture capitalists who are not investing their own money, right? They're investing the money of their investors, the LPs, right? The motivations of a venture capitalist are, they have other motivations besides what you're doing, right? So like you'd think with fundraising, all it comes down to is tell a story about how you're going to build this product, which is going to have this multi-billion-dollar market for it. And then the second thing is be credible in that story, right? So my story was pretty simple. General purpose platform reduces the cost by 100x or more. And, it unifies these things, which are currently done as like a dozen different tools. And No, I think I was pretty credible with Storm and my book and just being like a fairly well known and respected person in this field for which I'm building a product, right? Yeah. So it turns out those are maybe the two, those are important, those two things, but they might be the least important things in the fundraising process. To look at why investors actually invest. So, and what's funny is that I had already read all this stuff before about why investors actually invest, but I didn't really understand until I went through the process and went through these meetings where, and it was actually specifically Paul Graham that wrote about this stuff. Like he was writing about this stuff in like 2008 or something, or maybe even before that, right? But so the issue with investors, so there's other motivations with a VC. So first of all, they have their investors, right? And you don't see a return on investment for a long time, maybe 10 years, right? But you need to make sure that your investors, your LPs think you're doing a good job in the meantime before you get a return, right? On that investment. So you need to explain to them, well, here's the investments I made and why I made them, right? And so they have to be able to tell a good story, right? And usually, and what they're looking for is traction of some sort, either traction in the market, which is obviously something I did not have in 2019 because I was still building the product, or you're looking for traction in another way, such as, oh, this other big, well-known investor who's very respected invested in them also. So I co-invest with them, right?
Yeah.
So that's like the whole momentum thing that you hear about with it. And it's something that Paul Graham wrote about a lot, right? And so that's a major reason why investors, or that's like the main reason why investors invest, especially VC, is that they want to be able to, they want to see that traction so they can tell that story to their LPs, right? Now, as a founder, where I'm just trying to like build something cool and change the economics of software development, it's very frustrating to have to play this weird game where I need to like generate this momentum and social proof so that I can build momentum and finish my round. So that's like, it drives me crazy as a founder because like ultimately what, like a lot of these early conversations, I would pitch them and they'd be like, oh, this is great. Can you talk to these other people to see what they think? And they'd be really slow, like all doing all this like due diligence, which also seems completely unnecessary because like I told the story, I'm credible. What else do you need? Right. But really they're just delaying things because they want to wait to see someone else invest so they can tell that story to their LP.
So it's the first yes, that's the most important. Like once you get the first yes, the ones after that become relatively easier.
So the day I closed my lead, which was initialized, Gary Tan was the investor. Gary Tan's now the president of Y Combinator. But yeah, the day I closed my lead, everything changed. So now I was able to go back to all the other investors who were being slow. And I just wrote them a very polite email where I said, it's great that you guys are interested, but I'm looking to close the round now. Initialized is leading. Here's the price. Let me know how much you want to invest. You can invest anywhere between this amount and this amount. And let me know by this date. If it doesn't work for you, that's fine. No worries. Right. And basically what I'm telling to them is I'm not doing any more due diligence for you. I'm not gonna do any due diligence for you at all. So either you invest or you get out. Right. This is a polite way to say that. Or another way is to say like, stop wasting my goddamn time. I think a polite way to say that to them. Right. And man, it feels good to be in that position. You have the leverage and fundraising and not where you're no longer playing that game. Feels great. Right. So yeah, that was good. And what's interesting is that it was 4 days into my fundraising that I hit that point. So again, I wasn't like bogged down. It wasn't like I was bogged down for 6 months like a lot of founders are. Right. So again, it went very well, but yeah, it was not looking good up until that 4-day mark. And that's honestly, a lot of that credit goes to Gary Tan for not being like that as an investor, for really being able to understand the merits of something on its own and not needing all this silly momentum stuff first. Right. So, yeah.
Oh, congratulations on the successful fundraise, even though back in 2019, but congratulations. It's a huge deal for a company. So you mentioned like just during the fundraising period, you were thinking you might fail. Keeping fundraising aside, like it took 10 years in a way to build Rama, like starting from 2013 to now. Was there any point in this 10-year period where you just wanted to stop and do something else? Or what kept you going? Like 10 years is a long time.
Yeah. Well, I wasn't confident it would be possible until like 2016. Right. I think what kept me going is, the main thing is just like the opportunity to have this big of an impact on the world. like I wrote a blog post about this, about why I started Plant Labs, and like the thing that like I think, or something that really inspires me is the Apollo program in the 60s, the space program, because it was like, it's really incredible what they did. Like that speech that JFK gave at Rice University, like I've listened to that probably 50 times. Like I love that speech. It's so great and it's so like audacious.
Why
Like,
does
hey,
Rice play Texas? Sorry, I went to Rice, and then
yeah,
that was a real question. Like, why do we actually play them though? Like, it doesn't make. Sorry. Continue, please.
but yeah, I mean JFK was like, first of all, like the space program at that point, like they couldn't they couldn't even launch a rocket reliably. I think like 25% of them were exploding at that point, something like that. I may have the number wrong, but a lot of them were exploding. And to say that before the end of the decade, I think that speech was 1962, if I'm not mistaken, something like that. But to say before the decade's out, we're gonna have men walking on the moon and we can't even launch a rocket yet. And to say that on a national stage like that is unbelievable. And then they did it. They did it. And just like the way they did, like the engineering was incredible that they did. It was, I mean, it was brave what they were doing. Like those astronauts were like, man, like that was
Yeah.
scary to set up that time. Yeah, it was just the whole thing was incredible. And they really, I mean, they developed space travel and they figured out everything that goes into doing that and working in space and doing all that stuff, you know, setting the stage for all the stuff that came later, all the stuff we use space for, right? How much that's improved society at large and so on. So I just find that super inspirational, like pushing this frontier, not being afraid of it, and really advancing human potential. And like back in 2013, when I started working on Rama, that's what I saw with Rama, a way to fundamentally advance human potential. So more than anything else, that's what kept me going, that thing. As well as it just being a really interesting thing to work on just as a programmer, right? This new programming paradigm, figuring out how to enable abstraction, automation, and reuse in this aspect, this major aspect of software engineering, which has suffered so much in the past, you know, forever in these aspects. So at no point was I ever gonna stop. I mean, I would have stopped if I determined it wasn't possible, obviously, but at no point did I think it. At no point at no point did I get to a point where I thought it was not going to be possible. Like I was making progress over those first 3 years. Like it was definitely slow at some points. There were definitely some wrong directions, like some very wrong directions I went. But like, I think probably like, I remember when I was working on P states, like the abstractions for P states, especially for reactivity. That's something I understood from the beginning, just the importance of reactivity and how reactivity should be fine grained, where you get, when something changes, you get a very precise information of what changed, which is actually very different than how databases work, which are coarse grained. Like at best you would know that like, oh, this row changed, but it doesn't tell you what changed in that row. The fact that, oh, maybe this one value changed in this one way incrementally. Like this one value could be a set. So it could be this one column or this one row, this one set had this one element added to it. But actually all you know is it's this one row change, right? So that's coarse grained. Rama is fine grained, right? So you get precise information. So regardless of the complexity of data structures, you can do these reactive queries where it actually tells you that this set inside this map, inside this list, had these two elements added to it and this one element removed, right? So that's fine information, which is really powerful, can power some really interesting stuff on top of it, right? So it was working on especially like the API for P states and how reactivity could work, which really had me stumped. I think it was for like 3 or 4 months. And I went down the completely wrong path and eventually figured out that like I have to take a step back and question my assumptions here. And then I ended up figuring out what is the right way to do it, which was paths, this path model, which can do both non-reactive queries very efficiently and reactive queries. It's like, it was just like once, like, I remember the moment where that like clicked in my head and just being like, it's like an explosion in my head. It was like, it's so elegant. It's so perfectly enables everything that you would want from indexing, which is a very obviously broad topic. And there were other things like that, maybe not as extreme like that, of just this like, you know, 2 steps forward, 1 step back kind of process. But at no point did I think I wasn't going to succeed.
That is very inspiring, to be honest. And kudos on going that long and actually building Rama. It's really impressive. By the way.
Yeah. Oh, let me say one more thing about that. I'd say the thing that enabled all this was the fact that in 2013, I had achieved enough financial freedom that I knew I would be able to pursue this. I knew it would be difficult. It could take a long time. I didn't necessarily think it would take 10 years at that point, but I didn't really know how long it would take because it's such a broad thing to be working on. So the fact that I had some financial freedom, like I wasn't like, I wouldn't say I was like super rich, but I had made enough money from, I was part of a startup called Backtype, which was acquired by Twitter. That's why I know so much about Twitter. So I made enough money from that, that I was in a position where I could pursue a crazy thing like this. And that was a lot more appealing to me than doing something like a Storm company, which is just about monetization, just about making more money. Right. But we only have one life. Right. So let me do the thing. Let me do the thing that would make me like proud of my life, which is to expand human potential. Right. As opposed to just making more money than I already had. So that was, I think, the foundation that enabled this, this prospect.
No, that is incredible. I mean, it shows the path of higher resistance than the least resistance. It would have been easy to be on a path like either start a company with Storm or even like, let's say, be a distinguished engineer or technical fellow at one of these big companies and still make a lot more money with that. I mean, you had the credibility to back that up.
Well, I would have made more money in the past 10 years if I went that route. I think Red Cloud Labs is worth way more money than that could possibly be. But again, like resistance, it depends how you define resistance for yourself and really what you want to achieve from your life. Like for me, like being so inspired by something like the Apollo program, like it wasn't even a question which path I should take. Right. Like it's like I actually feel that doing the Red Cloud Labs path was less resistance for me. It's just like less like internal resistance.
Because
I had this idea for Red Cloud Labs and I decided to pursue a Storm company. Well, then that would be eating at me forever.
This is
right?
the regret minimization framework that you refer to in the blog post, right?
Yeah, that's the thing that Jeff Bezos said, right? Where he was in, like his situation when he started Amazon was similar, right? He had a really high paying job, very comfortable job. I don't know where he was working before he started Amazon. Then he had this crazy idea for this online bookstore. And then, he said that like, so which way do I go? Do I take this leap or do I just stick with my comfortable lifestyle and job where I'm making a lot of money, right? And then he framed it in terms of regret, right? Where he said, I would never regret trying the bookstore thing, but I regret it forever if I didn't, right? And I'd say the same mental process went through me as well.
So a couple more questions before we close off. You've been building Rama, which is a deep technical platform. At this point of the company, it's about, as you mentioned, like you started building the team in 2019, and now it's about scaling the team, building the company culture. Can you share more about how you are thinking about the company building aspect of things, which is slightly different from building deep tech?
Right. Yeah. Well, I've learned a lot. That's something I've learned a lot over the past 4 years. So from the start, I did decide to do a fully distributed team. I actually think that's a much better way to run a company. Obviously, a lot of people had to experience it during the pandemic, and unfortunately, they experienced. So, like a distributed team, first of all, requires people who actually want to be on a distributed team. So, one of the reasons that the fourth distributed team of the pandemic didn't really work that well was because those people wanted to be in an office, but they weren't, right? So, that's a really big aspect of it, right? But I do think that productivity and collaboration and whatnot are better distributed, presuming that everyone wants to be distributed.
Do you guys still work in the same time zone or everything's in writing?
No. So I do find it important to be in close enough time zones that you can still do video calls.
Got it.
So so we don't really hire globally. Initially I was intending that, but I do think it's important to be close enough, but it's still a pretty wide range, right? Yeah. So I actually changed, when I moved to Hawaii, I changed my schedule. So now I wake up at like 5 a.m. and p.m. right? So, but it actually turns out to be a great lifestyle to lead in Hawaii because mornings in Hawaii are incredible. It's not too hot yet. Doing stuff outdoors is amazing in the morning. But basically we work on an East Coast time zone, right? So whenever we talk about like times internally, we just assume East Coast, right? So 2 p.m. means 2 p.m. Eastern, which would be 8 a.m. Hawaii time. So, but yeah, obviously across that range of time zones, like it's still a huge portion of the globe that you can hire from, right? And I do think that's one of the like really major advantages of distributed over co-located teams is the fact that you're able to hire from a huge portion of the globe instead of just this one city, right? Whereas you can only hire from, and co-located, you can only hire people who are already in that city or who are willing to move there. And if you're looking for experienced engineers, well, chances are they don't want to move because they have a family and that's somewhere where they are, right? And I have found that the best engineers kind of come from the most random places and live in the most random places, right?
Yeah.
Yeah, that's just something I observed over my whole career. And so when you say I want to be co-located in, let's say San Francisco, which is obviously a very common place to have a startup, well, you are severely limiting your talent pool. Consequence, it means that quality of engineers will be less than they would be if you're distributed, just because you have access to so many less engineers. So I think that's a major thing. Although I do think distributed is still better, even without the recruiting aspect being such a huge advantage. Yeah, like some of the problems in a co-located team, like if you're co-located in an office, is just like distractions, right? Programming requires focus, and an office environment is kind of inherently unfocused, like with distractions. There's office layouts which are better than others. The most common office layout, of course, is the open office. Well, it's been a long time since I've worked in an office, but I presume that's still the most
Yeah,
common
it
one.
is.
And yeah, it is. It is. You literally, it's like an open office is if you decided like I am going to design the worst possible environment for programming, like I'm going to engineer the worst possible environment, and that's what you would end up with is the open office. People walking around, the bathroom door opening and closing, people chewing on chips next to you, people having a great conversation, like really hard to focus in open office. We have that like running joke, which everyone's heard of like, oh, I get all my work done after everyone's left the office. All right. Well, then don't work in an office just if that's the case. So anyway, that's one of the core principles of just like Red Hot Lab company is a fully distributed company. And of course, I was inspired by other companies that were doing it and having a lot of success with it, just to see that was possible. And, it's worked very, very well for us. We basically have a morning meeting where we kind of sync up in the morning as a stand up. We also do a fun thing. Every morning we do something called question of the day. So every day we rotate, and when it's your turn, you can either ask a question to the rest of the team, like something personal, or or you can also do share of the day. Like you can just share something interesting about yourself or something you found. And, we've been doing question of the day now for 4 years. So the questions have gotten like really weird and esoteric, which is really fun.
Can you share
Wait,
an
Wait, what?
example
Yeah.
question?
Man,
A weird one,
I
please.
think the recent one was like, I don't know if this is weird, but it's esoteric.
Yeah.
It would be like, what's a story from one of your parents' childhoods? Yeah. Which is like kind of an interesting question. I don't know. I don't know if it tells you that much about the person, but it's an interesting thing. And people have really, I gotta say, we've heard some pretty wacky stories from people. Or like, I don't know, one I asked a long time ago, I remember was, I asked this twice. So one time I asked, what's a mystery in your life that you haven't solved? And another one was, what's a mystery in your life that you did solve recently? So all sorts of wacky stuff from that one. And I think the idea behind question of the day is that like, when you're on a co-located team, you kind of naturally get like camaraderie because you go out for drinks after work or you get lunch together or whatever. So you naturally just have a lot of like socializing, right? Whereas a distributed team, you have to be more intentional about it because it doesn't happen naturally. So question of the day is a way for us to just like be people to each other as opposed to just screen names, right? And likewise, that's also why I think pair programming is very important in a distributed software team.
That's
Whereas
cool.
I don't think pair programming is really that important, at least not important as like a regular everyday process on a co-located team. It's like we pair every day. And when we pair, it's not like two people or it's not like you're working together as equals on the project. It's one person is driving the work. It's whatever. So like one person will drive, the other one will follow. It's the driver's project, right? And as a follower, you're there to see what they're doing and then to maybe help out if you can, maybe talk through some design issues. But mostly it's just about having individual face-to-face time with your teammate so that you build that camaraderie. So like I say, that's the main goal of pairing. We pair for one time for 45 minutes every day. And the second goal is just knowledge sharing, right? So now you're learning about this aspect of the code basically pairing with. Knowledge sharing is like something that like I've thought about a lot like ever since I started building a team, because that's one of the primary problems you have to solve in building a company. So I've learned a ton about that. Like there's a lot of stuff we do for knowledge sharing. Some of the stuff we do for knowledge sharing, I think one of the best processes we use is something we call reverse story time, where that is where, and we rotate this every month, whose turn it is. So we usually do this once every, like, I'd say 4 to 6 weeks. But when it's your turn, you have to give a presentation on some part of the code base that you did not build, something someone else built. So this accomplishes 2 things. First of all, the best way to learn something is by teaching it. So that just does that. And it gets that subject taught from a new perspective, and more importantly, from a beginner's perspective. And so we record every reverse story time. Now we have like an archive of like tons of them. I don't know, probably more than 30 at this point. And also that's a really good resource for new employees to be able to learn, right? They can watch these 30-minute reverse story times and actually learn the different aspects of the code base.
That's super cool. I mean, that also, I don't know if I know someone, my code is going to get read by someone trying to trace back and to get blames. It keeps me more on my toes, I think. Not do anything too stupid. Yep, yep, yep.
Yeah. Yeah. So those have been good processes, and, and we've adjusted over time. Like, so for stand-ups, we used to just do it like live. So we just go around, everyone has one, and you just give your update. And actually recently we changed that. So we still do the stand-up meeting, but you give your stand-up update in an email beforehand.
Yeah.
Yeah. And so now, first of all, it shortens the length of the meeting, and it creates an organized place where you can have further discussions about whatever the stand-up update is, right? So someone update about some part of the system, like, oh, I'm taking this approach for data transfer. And then maybe someone will respond to that email and create a thread of like, oh, why are you doing it this way? Have you thought about this? Whatever, right? So that's been a great addition. This has been a great, like, small change to our process, but I think makes us work more like efficiently a little bit. So now the stand-up update is more, or the stand-up meeting is actually about doing the question of the day, and then, deciding what is the pairing session is going to be for that day. So it's usually like, now it's like a 15-minute meeting or whatever, and then that's it.
That's really cool. Like we tried that on our team a while back, and this was during the pandemic, where we switched our stand-ups from like all in person to like 2 days a week we would do over a call, and 3 days a week it's like a Slack bot will ping you like what you got done, what you're doing today, what you need help on, and whatnot. We found as a team that was an extremely effective way for both sides, actually, for people who were writing the bit, because they got a chance to think about what they did and what they're planning to work on, and specifically ask help on certain parts, like, hey, I want to discuss XYZ. And that they're exactly the thing you described, like a bunch of threads after the stand-up, and was very effective for people consuming that information too, because when you're starting, some people are sometimes not paying attention, so they miss it. Anyway, totally agree on that.
Yeah.
Oh, this has been an awesome chat, Nathan, and thank you so much for being so generous with your time. Before we close, is there anything else you would like to share with our listeners?
Man, nothing's come to mind. We talked about everything from home to Rama.
We'll include the blog posts in the show notes.
Oh, for sure.
So people can
For sure.
reference it.
Yeah, sounds good. Yeah.
Yep. Can we hit Nathan with our question of what's your favorite software misadventure?
For a misadventure?
Oh, another way to think about that is, what's a failure of yours where you learned the most?
Yeah, I mean, in the development of Red Planet Labs, so that thing I described about going the wrong direction on the P-State API, and just, that was probably the biggest misstep, I think, or just like, basically that whole 4 months could have been. Okay, so what made that like a particularly big misstep is that the whole path abstraction I'd already developed. So so Rama's written Clojure, and in just developing Rama, just developing the paradigm, writing a compiler and whatnot, I needed to develop this path abstraction just to make it easier, just to do just that regular stuff, that regular permanent stuff, just to be able to just work with data structures more easily. And Clojure for you guys know Clojure?
I know it because of you. You talk to us,
Clojure, it has immutable data structures. So you're always working with immutable data. And it's really cool how it works. Like you take a map and you add a new element to it. It actually returns you a new map instance, but it's very efficient. Basically, it shares structure between the two instances, which is how it's efficient. But it has this implementation for vectors and sets and other data structures as well. And so a lot of stuff in developing Rama, I'd end up with like a set inside of a map or whatever, right? And it was very cumbersome to manipulate structures like that. And actually in the compiler, it was much more, it could get very complicated where the code that you're writing is actually a graph computation. It's a data flow graph, right? And sometimes some of those nodes actually have a data flow graph within them. So complex structures that I needed to be able to do compiler analysis on, where I have to do traversals and very complex nested manipulation. And everything is immutable, right? I want everything to be immutable because there's just so many advantages to having your data be immutable. So I developed this library in Clojure called Spectre, which was this path API for generically querying and manipulating arbitrarily compound structures, right? And it's like super fast as well. So I actually already had Spectre, I already had the path abstraction. And so I went down this path of the peak state design where I was thinking in terms of like, okay, I'm literally going to have a map P state and literally have a set P state and literally have a list P state. You compose them together, but then you manipulate it by calling get or get the nth element or whatever. And then I'm going to have reactive versions of all these queries. So I have get and get reactive and so on. And then you try to compose it like that. And it just was not working at all when I was trying to actually use this approach to actually express my million use cases that I had. And then ultimately I realized like, well, P states are nested data structures and Spectre and PAS are all about being the most expressive, powerful way to do persistent data structures. Why don't I just use PAS on P states and bake the reactivity into PAS themselves? And that was the big moment where suddenly everything fit together. And then I was able to scrap everything I did those 3 or 4 months and then take this new route. And so, yeah, like on one sense, it's like, feels incredible to have this breakthrough where I just found like a fundamentally better way to interact with an index. And it not only is generic and very concise and elegant, regardless of the complexity of the index. So not only like like every data model that exists, but any sort of permutation you can have with data structures, it's super elegant. And it has this new capability of arbitrary fine-grained reactivity. It's a major breakthrough in those 2 respects. But then in another sense, you feel really stupid that I already had PAS for a long time and that I went down this long road, right? But yeah, I'd say that was a pretty big, that was definitely a misstep.
No, but to your point, every time when I get stuck on a really hard problem, I think about how nice it will feel like once I actually, solve it, if I can.
Yeah,
Yeah.
I gotta say it was like when we first had, when I had our Twitter scale Mastodon instance running for the first time at scale, like very, very high performance, that felt good because there was so much that went into that. So
Yeah, that must have been a realization of all the work that went in, I imagine.
Yeah, it was kind of the culmination. That was the culmination of the original vision,
Yeah.
right? To be able to build an application like that, which is so costly otherwise, at such low cost and at such high performance was
Yeah,
great.
that's pretty awesome. Well, we'll add links to Red Planet Labs, Rama, and to your blog post in our show notes too. And we'll also link your Twitter or X profile where people can follow you and learn more. And for everything today, Nathan, thank you so much for taking the time. This was awesome. We learned a lot about Rama, about you, and I'm sure our listeners will too. And we highly encourage them to go check it out.
Awesome. Great talking to you.
Thanks so much, Nathan.
Thank you.
All right.